Okay, so welcome everybody to our last seminar before holidays. So today we have David, that I think you know already very well. No. And it's an introduction, so whenever you wish. Okay. So I don't know exactly what is the rule for the seminars. 45 minutes, 50 minutes?
You've never been in a seminar here. That was very bad about it.
No, but the organizers have changed recently.
That is also true.
Following the feedback of students, we have tried to reduce 45.
Yeah,
it's okay. I'll try to fix that. Okay, so I'm going to present you two contributions which we have done in the field of thermoelectricity. So I'm not an expert in this field. I mean, I just started to work in this topic since 1 year ago, more or less. So I don't know if any of you is familiar with this. So, okay, in case you have ideas or whatever, just we're happy to discuss. These two works, okay, one of them is purely theoretical, okay, so it's just a prediction, what we have done in Mesoscopic Conductors regarding asymmetry in Thermopower. So this has been done in collaboration with Lorenz, as you know. And then the other one is a collaboration with an experimental group, the head of which is Heine Licke from the University of Lund in Sweden. But okay, all measurements and let's say analysis have been performed by Jason Matthews from the University of Oregon. He already got his PhD just a few months ago. There are two, let's say, one main common characteristics between these two works. Both of them are related to a kind of asymmetry which Seebeck coefficient presents in these mesoscopic conductors. Okay? In one case, in the experimental case, this symmetry is related to some spatial asymmetry which is broken by means of some scatter that we have in the sample, okay, some obstacle impurities. And the other one, the theoretical work, I mean, the main idea is that the thermopower in multiterminal structures becomes asymmetric in the presence of volgate. Okay, so in both cases we have asymmetry, okay, but in this, the origin of this asymmetry is different. Okay, I think in these two cases. So I prepared a very just broad introduction to an introduction, which also I think was also useful for my self-education in this field. So this is really basic stuff, okay? Maybe also useful for undergraduates. So what is it all about? So we have a thermoelectric device, okay, just a piece of metal, a conductor, and then we heat one side of this, let's say, roll bar, okay? If we do so, then this would be like your hot side, and that would be your cold side, okay? So we know that this thermal gradient will drive a current through the conductor, okay? And then you can use this current, for instance, if your setup is, let's say, in open circuit, then you can use this gradient or this current to generate some voltage, which you can use for some useful work like okay. Actually, this is not just a cartoon. Okay, the first experiment done by Seebeck in the 19th century was very similar to this, right? So he had a conductor here, and then just in the proximity of a candle, then he was able to heat one side of this conductor, and there was a current. Okay. Instead of this light, he had a compass. Okay, and then he noticed that the needle of the compass just changed orientation. Okay, when he was heating this side of the sample. First he thought, okay, maybe with temperature linears we can use a magnetic effect. Okay. But then the explanation was that you're inducing a current, and then due to Ampere's law, then you can produce a magnetic field, which in turn changes the orientation of the movement. Okay? But that was the first experimental demonstration of such an effect, and it is quite old. And so, if for simplicity we consider a two-terminal conductor, okay, so we can generate current in two ways, right? By just putting a battery of a voltage or a temperature gradient. Okay, this voltage is always assumed to be above some average electrochemical potential, okay, which I call Fermi energy. For the temperature, we can do the same, right? So there is a temperature gradient which we put, let's say, to the left side, okay, on top of some uniform, some average temperature in the system, okay. And from the right terminal or the right side would be just your cold side. Then the current in linear response, so it is not clear, of course, that this linear response is valid here, right? But just suppose for the moment that we can express the current just by using linear coefficients in the forces, okay? So we have a current which would be proportional to the voltage that we apply and to the temperature bias that is present in the conductor. Of course, then in front of these forces or fields, you have the responses of your system. Okay, so you have the conductance, which is the response to a voltage shift, and you have this L coefficient, which has to do precisely with this thermoelectric response of the conductor. Okay, so the Seebeck coefficient is defined in such a way that, as I said before, the conditions are in open zero. So there is no current flowing through the sample, so you put here 0, and then the voltage generated between the sides of the conductor divided by the temperature that you are applying at the conditions of 0 net current, that's the Seebeck coefficient. Okay? And in this linear response theory, then this is just given by minus the conductance divided by the thermoelectric response. Okay? Nowadays, good thermoelectrics have Seebeck coefficients of the order of 250 microvolts per Kelvin.
Why the minus sign?
Oh, because I define it without the minus here. I put here 0, and then you. Okay. So sometimes you can define it with a minus here. So as I said, good thermoelectrics have this order of magnitude for the Thermopower. Okay? So the voltage that you are able to generate by increasing 1 Kelvin your gradient is of order 0.2, 0.3 millivolts. So it's not really a big thing. So it's just a small thing. Okay, but still it can be measured. Now you can do the same with the heat flux. Okay, so of course, when you are transporting charges, you can also transport energy. Okay, so the heat flux can be written also in terms of the voltage, applied voltage, and also the temperature gradient. Okay, with some coefficients N and K. Okay, K would be the thermal conductivity or conductance, and M would be just the response in terms of the heat flux to a change in the voltage. However, experimentalists prefer to write the second relation in a different way. So they prefer to write, instead of voltage, they prefer to take as an independent variable the current. Okay? And so the heat flux will be given by some coefficient, pi, plus the thermal conductance times temperature. Okay? And we know since Kelvin and Onsager that these coefficients L and M are related to each other, and then the, let's say, voltage generation due to temperature change, which is described by the Seebeck coefficient, is related to this big pi, which is related to itself to the Peltier effect. Okay, why Peltier? Because Now you can do a similar experiment, but now instead of looking at the electric charge, you look at the energy charge or the heat flux if you are dealing with charges. Okay, and then you can put here, for instance, a 0, and then you can drive a current like in these kind of devices, so that you can actually pump or absorb heat. Okay, in this way. So the effect for the Peltier the Peltier effect, which is a kind of cooling or heating effect, is really connected to this thermoelectric generation. Okay.
Just one question. So, how is this related to the different materials in the conductor and the wire? Isn't there some relation?
Yeah, so far, I mean, we're really simple. So I just consider one material here. Of course, now if you go into the details, you have to take into account 2 dissimilar metals and so on. I'm just telling you just a basic, very basic idea. Okay? Now, what happens if you now include a magnetic field? Okay, then the Eusager relation, reciprocity relation, says that the Peltier coefficient and the Seebeck coefficient are also related to each other, but you have to invert the magnetic field. You have to invert the orientation of the magnetic field. For the other hand, this reciprocity theorem tells us that the conductance for a true terminal setup is an even function of the magnetic field. So when you change the magnetic field, the conductance should be invariant. So what happens with the thermopower is also invariant when you change the magnetic field? Is an even function of the magnetic field or not? So that's one of the questions that I would like to answer during this talk. But before that, I would like to tell you just kind of motivation for working in this field. Well, the first motivation is just that now, due to energy harvesting issues, you want to be able to extract energy for some waste heat that you have in your devices. Okay, so then these devices, thermoelectric devices, this is not new, of course, could work as a converter from heat to electricity. Okay, you just take heat. Okay, for instance, here in this car, this is just a real car. So, and here they put in the exhaust pipe, they put a thermoelectric device, and not all, but some of the heat which is produced by the engine can be transformed into electricity, which can be used for something else. Okay. Since this thermoelectric effect and the Peltier effect, this cooling effect, these are related to each other, then you can use these thermoelectric devices not only for converting heat to electricity, but also to, let's say, pumping heat or cooling. Okay, I just showed an example before. This is, I think this is really nice, and there has been a lot of research in this field, because it has, it offers a lot of advantages compared to, let's say, mechanical coolers that we have at home or in industry. Okay. First of all, it contains no moving parts. Okay, so you have to just connect it to some circuit, and that's really good, because then you don't need to basically to repair your device for years. Okay. However, there is a problem. As I said, the effect is small. Okay, so the efficiency of these devices is not very good. I think that the power they are able to release is of the order of 10, 20 watts, which is not a big thing. Let's say for heating or for cooling your home. And from the fundamental point of view, let's say maybe more interesting for physics, is that using the thermopower, you are able to distinguish between the electric charge which is carrying your current into the metal. Okay, so I will explain this in a moment, but it is possible to see that the thermopower is negative for electrons and positive for holes. So just by measuring the thermopower, then you can tell whether you have electrons or holes. Okay, usually experimentalists do this by just putting the sample into in the middle of a magnetic field, so they measure the whole conductance, but sometimes you cannot do that. Okay, and this is a different level. Okay. Now, to measure the efficiency of these coolers or the converters, there was a suggestion in the late 40s to quantify the efficiency, which is given by this figure of merit, okay, which is called G. And this is given by the square of thermopower, of the Seebeck coefficient, times the conductance divided by the thermal conductance. Okay? Now, this is, so remember that S is voltage divided by temperature. Okay? So this is voltage square times conductance, which is, this is a power. Okay? This is like a joule key, which is V square over resistance. Okay? That's a power. So that's the power that you can generate with your device. On the other hand, this is thermal conductance, which is the heat flux divided by temperature. Okay? And then this is the amount of energy per time. Okay? And then this is already power. Okay? So this let's say the motivation for introducing this Z is precisely this ratio. Okay? So it's the power generated divided by the heat energy that you are using by applying this temperature reading. Okay? It seems that to be able to compete with present day coolers, then one should have this figure of merit of the order of 4. So C times temperature, you have to multiply temperature so that this guy becomes the measurements. Okay? So C times T should be on the order of 4 at room temperature. Okay? Nowadays, the best thermoelectrics have a order of 1 or 2. Okay? So there's still not enough to reach this value. So what do we need to have a good thermoelectric or a good cooler based on thermoelectric or a thermoelectric device? So you have to increase this ratio. So you increase either your numerator or decrease the denominator. Okay? So the numerator is proportional to the electric conductance. So you need to have a good electric conductor. On the other hand, the denominator tells you how difficult it is to maintain this temperature reading over time. Okay? So you need a bad thermal conductor. Okay? So if you are able to find good electric conductor and a bad thermal conductor, then you should have a big figure of merit. Okay? But now remember the Wiedemann-Franz law, which says that the thermal conductance divided by the electric conductance for many metals, this is just constant. So it's very difficult to increase this G and decrease GT at the same time. Okay? However, this law works well for free electron. I mean, for free electron metals can be demonstrated. It's really good for solid-state physics. But of course, what happens when you include electron-electron interactions? Then this law is no longer true. Experimentally, it seems that it works rather well both in the high and the low temperature regimes. With intermediate regimes, there are deviations from this rule. And then this ratio here becomes temperature dependent. And so there is some hope that this can be changed. But there are more bad news, because so far I have just considered just charges, okay, electrons or holes. Okay? But these, of course, contribute to the electric conductance, but we have the thermal conductance, and in your metal usually you also have phonons. Phonons do not carry electric charge, or do not degrade the electric charge, but they do contribute to the thermal conductance because we can carry energy. Okay? So this G is in reality the sum of two thermal conductances. One from the electrons and the one from the phonons. Okay? So you have to have a good electric conductor, a bad thermal conductor, and try to suppress the contribution to the photoresist. These more or less can be done using interfaces and kind of in the nanostructured materials, okay? But then there was a work in the 1996 from Macon, and there was a prediction that if you consider if you have a conductor in which the density of states is dominated by kind of singular peaks, okay, very narrow peaks, then he demonstrated that this factor essentially grows without limit. So there is no, let's say, physical limit why this CT should be bounded from above. It should be bounded from below due to some thermodynamic arguments. Okay? But from above, I mean, there is no reason why there should be no crystal, no system with a big CT, with a big figure. Okay? When he wrote that, he was thinking of these rare earth materials, which now become kind of political debate in China and so on. These materials have these F levels. These levels are really deep into the ion. Okay, so the contribution to the total density of the states are in terms of these very narrow peaks. Okay, and then he gave some estimation in terms of CT of the order 10, 20, so 10 times larger than the normal conductors. But in nanostructure we have a system, which is the quantum dot, which also shows this singular density of states. Okay, so these two things somehow motivating us to study thermoelectricity in nanoelectric or mesoscopic conductors.
David, to me at first sight, this, ZT going to infinity, we shouldn't be somehow in conflict, at least very naively, with the second principle of thermodynamics, because you say, so I can generate a very high power, because this is using a very low heat energy.
Mm-hmm. No,
this is like a Carnot engine or whatever.
Yes, the Carnot efficiency can be related to this with this figure of merit. Actually, I want to tell you this a little later, but the maximum efficiency can be related in terms of this CT. So if you know CT, then you know also your maximum efficiency in terms of the Carnot efficiency. So,
but I'm speaking more the fact that it's not bounded from the wall.
No.
It seems surprising to me.
No, it's
you can use negligible heat energy to produce an enormous power, right?
No.
If ZT goes to infinity, numerator very big, then denominator very small.
ZT goes to infinity when you have T not fixed. ZT does not go to infinity.
This of course depends on temperature. Because these factors here depend on temperature. Okay, maybe later.
Okay.
Okay, so that was the motivation to introduce mesoscopic conductors. Okay, so we follow the Landauer-Büttiker approach. Okay, so in this approach, the typical length associated with quantum conductors is the smallest of all energy lengths. Okay, so this is of the order of nanometers, let's say, and the length associated to phase breaking processes, or the length associated, or the mean free path, or inelastic processes, these are larger. Okay, so let's say the current, okay, or all transport properties are determined by the scattering properties of the small conductor. So you have to imagine this as just a small piece of metal which is attached to massive reservoirs. Okay, so these reservoirs, these metallic terminals, all inelastic processes, all dephasing processes, everything take place there in the reservoirs, not in the small conductor. Okay, that's why let's say electrons, where they get through these nanoscopic conductors, they keep the quantum mechanical character, let's say, and then the current is given by the transmission probability to get through this Mesoscopic conductor, okay, times the difference, the occupation, okay, between left and right. So that's basically the main idea of this approach. Okay? It's the descriptive approach. Now, you expand. You now have, let's say, as before, right? Let's say the left lead. We apply some voltage and some temperature. So we expand this around equilibrium, and then it is easy to see this the thermopower, which is given in terms of this ratio between these two intervals. Okay.
Sorry, the T is transmission and also temperature.
Yeah, sorry about that. Sorry about that. When the transmission is a function of energy, or T of E is transmission. And this T alone is yeah. I would change slightly the notation later. So we have transmission here times energy minus the Fermi energy, and here we have the Fermi distribution function evaluated at equilibrium. Okay, the derivative. Okay. Now. This is just a general formula, okay? And now, what you can do, if the transmission is not very strongly dependent on energy, for instance, you don't have any resonances, or you're far away from the resonances, then you can make a Sommerfeld expansion, okay, in powers of temperature, and this is your result. So the thermopower is just the derivative, energy derivative of the logarithm of the transmission, evaluated at Fermi. Okay, so it depends weakly on the energy dependence of the transmission. It goes to zero when the temperature is zero. Okay, and another interesting thing is that the derivative of the Fermi function in equilibrium is even with respect to the Fermi energy. This function is odd. Now, when the transmission is also even, when it's symmetric, above and below the Fermi energy, then the thermopower is zero. When do you have this kind of symmetries? For instance, you have particle-hole symmetry. Okay? If your system has particle-hole symmetry, then independently of the temperature, the thermopower is also zero. That's why you can distinguish between electron and holes in the using thermopower. Because if you're able to build a system with a particle-hole asymmetry transmission, then the thermopower is going to be different from zero. Okay. So these are examples of materials that we have in mind. Okay. For instance, quantum point contacts, which are just supposedly two big metals, and then you put small hole in between them. Okay. So it's like a constriction between two metals. So electrons can flow through these constrictions. Only if you have the Fermi wavelength that can fit into this small channel, okay? Or you can think of a nanotube, or even molecular junctions, okay? And thermopower has been measured in all these systems. For instance, in the first one, there was some peaks in the thermopower related to every time that the conductance becomes quantized, okay? So if you increase the Fermi energy, then you can feed more and more waves into your channel, okay, and the conductance becomes quantized, and the thermopower has this series of peaks. There were some experiments in the early 90s. Now, for nanotubes, the thermoelectric power as a function of temperature is linear, okay. So, in agreement with this formula some people call the mode formula because there is a similar formula in semi-classical field. Okay? It's just the derivative of the conductivity divided by the conductivity. Okay. And recently there was also measurements of the thermopower when you put a molecule between gold contacts. Okay, and here the molecule is belongs to the family of benzene, some ring here, and they can change the length. Okay, but they're changing the type of molecule. Okay. And they could measure the thermopower. All of them are more or less of the same order, okay? Around 50 microvolts per Kelvin, 10 microvolts per Kelvin. That's more or less the order of magnitude. Okay?
This is of the same order as in metallic thermopower.
I think it's slightly disorder. But these are the first experiments, okay? Okay, so Since we are now interested in multi-terminal, I've been talking all the time about two-terminal conductors. Okay, just this two-terminal, but I want to just extend this to multi-terminal case. Okay. Now, then the formulas look a little bit more complicated, but it's essentially the same. Okay, so you have to sum over all your reservoirs. Okay, and then instead of just having one response coefficient, then you have a matrix. Essentially, it's the same. And then you expand around the equilibrium point for both voltage and both temperatures. Now the temperature according to the theta, try to distinguish the transmission. And then, okay, this was done by Butcher in the early 90s. Okay, so you have a formula for all the conductance and all these transmission coefficients in terms of the transmission probabilities and the Fermi distribution function. Okay, that's once you know the transmission, then you are able to calculate all these coefficients. Okay. Now let's explain you the experiments. Now the experiments is like they call this a ballistic rectifier. So they have two channels which are crossing around here, one point. Okay. So you have electron flowing either this way, or also from above or from below. And in the middle of this cross junction, they put a scatterer. They do a scatterer, and they have the shape of a triangle. Okay. So what do you expect here? If you now put your, let's say, if you just inject electrons from 2 or from 1, then the electrons will prefer, just because this breaks your symmetry, will prefer the trajectory which is deflected to terminal number 3. Okay? So if you have more electrons accumulated here than here, then you will have, if now you measure with a voltmeter the voltage between 3 and 4, you will obtain a voltage drop between 3 and 4. Okay? I think that's more or less clear. But now what happens if you now invert the current? You will obtain essentially the same. Okay? So the current, or let's say the voltage at I, the voltage at given current, when you invert the current, the voltage is essentially the same. Okay? So this can work as a rectifier. So far, there is no temperature applied to the system. Okay? But now suppose that you, instead of voltage here, 1 and 2, you apply temperature. Okay? So there will be like your hot spot, and then you have a cold spot here. Okay? Then, again, electrons will be injected here, and you should observe a thermopower transversally to the direction of the current. Okay? Okay, so this can be seen as an Ernst effect. Okay, but here, of course, the magnetic field is zero. Now, these are the results. Okay, so this is the voltage drop as a function of the heating voltage. Now they measure 4 harmonics. Okay, omega squared, omega mu cubed, etc. Now, the largest of all these 4 harmonics is 2 omega.
Sorry, what is the heating voltage?
Sorry, I didn't say this. Here you have a secondary circuit. Okay, so you apply to this side of your. Okay, this side is far away. Okay, but here they put some AC which heats this part of the sample. So you expect that the temperature here will be higher than here. So
they measure the voltage used to heat, but it's not they don't measure temperatures.
No. Okay. They just because they cannot put a thermometer. Okay, so they estimate the temperature, let's say. But what they see is that this voltage drop as a function of heating voltage, the largest contribution comes from 2 omega. Okay? And this is consistent to the fact that this voltage drop is proportional to the square of the heating voltage, right? Because temperature appears because you have Joule heating. Okay, so for Joule heating, just V squared over some resistance. Okay. And another thing is that it has some square fitting or contribution to dependence with heating voltage. Okay. So this is, let's say, the first, as far as we know, first demonstration of a transversally generated thermal power in a mesoscopic sample. Okay? But okay, it was more as expected. Now, you do something more interesting. Instead of hitting the right thing, which is this formula, this curve here is exactly the same as this one. Right? Now, instead of hitting the right, you now increase the left. Now, if you increase the left, then you will spend more or less the same thermal power, right? Because then electrons will now come from the left, and they should accumulate here on the top, right? But however, the thermal power just changes sign. And now they hit both channels at the same time. And then, on average, you should not observe any thermal power at all, because then the net current should be zero. However, they see a small sign. Okay? These expectations are based on the fact that you have left-right symmetry here along the triangle. You break the up-down symmetry, but you allow for left-right symmetry. Okay? Now, then, where these symmetries come from? Okay, we extend this, as I said, multiterminal scattering approach, and then, okay, I can tell you the final result. If you put, you have to solve your system of equations with these conditions, that the current through terminal 3 and 4, which are your voltage probes, no current flowing through these probes, then they are zero. Okay, and then you have temperature applied only to 1 or 2. Terminals 1 or 2. Then this is your voltage, okay, some complicated formula. But then these B coefficients, okay, now forget about this A coefficient for the moment. This B coefficient have this awful form, okay, in terms of conductance coefficients, L coefficients, etc. So it's a little bit complicated. But you have a contribution, let's say, asymmetric in the thermal gradient and antisymmetric in the thermal gradient. And this contribution, which is antisymmetrical in this gradient, appears because you have asymmetry between left and right. This LT1 minus LT2, here T means 3 and here T means 4. Okay? So this is suggesting that there is no such a left-right asymmetry in the sample. Okay? And this is the only way to explain this change of sign when you invert the temperature reading. Okay? So this is kind of proof that using thermal power, in this case transversal thermal power, you are able to detect the asymmetries, the spatial asymmetries in the conductor. Okay, so, okay, still 5-10 minutes.
Yes. 15.
Okay,
15.
Okay.
The harmonics that you have drawn
Yeah.
in the previous pictures, or
This one.
where they are from, these harmonics, what they represent? Or?
I mean, they apply an AC field
Okay.
to
There is an AC
heat the
inside
side.
now,
Okay?
yeah.
And from the AC response, they just
Okay.
detect these thermal contributions. Okay, so that was the experiment. Okay, now I would like to tell you a little bit about the theoretical work. Now, in the previous experiment, I said nothing about inelastic or dephasing effects. Okay? Because I said, okay, all inelasticity, all dephasing, everything happens just very far away from the conductor, from the nanodevices. Okay? It just takes place in the reservoirs. But of course, in reality, you could have elasticity or dephasing. For instance, these molecules here, they vibrate, okay, or the nanotube, okay. So you can have your electron coupled to form modes, which can use dephasing. So you can have many of these effects taking place into the nanoconductor. So. We want to model these incoherent effects. Okay? How do we do this? Well, independently of whether we have this system, which is a chaotic cavity, or this system, which is ballistic junction, very similar to the experiment. It doesn't matter. We need a microscope to describe the microscopic mechanism why the electrons suffer from dephasing or inelastic process. Of course, this is very difficult because then you have to put in your Hamiltonian description interaction with phonons, interaction between electrons, which are supposed inelastic transitions, or if you have fluctuating impurities, whatever you like. Okay, and this is very complicated. And on the other hand, you would like to see some, or to study some universal properties. Okay, so in the late 80s, Buttigieg invented the voltage probe model, which consists on the following. Suppose that you have a nanoconductor, and then you have two terminals, two big reservoirs, as before, and now you want to induce some decoherence into your sample. Okay, then you can just add a fictitious terminal. This is not real. This is purely fictitious terminal with a given voltage and a given temperature. Okay, and now you say that the current through this terminal is zero. It's like a voltage probe. Okay, so if the current through this is zero, all electrons which come from, let's say, terminal 1, finally they will exit the sample through terminal 2. Okay, but in their way they could be absorbed by this probe and then re-emitted again with a totally unrelated phase. Okay, that's kind of a way of clever way of inducing the phasing into the sample. As I said, this is totally fictitious. Okay, so the only difficulty here in this method is that it introduces some consistency. Okay, in the equations, because now you have to adjust this voltage V3 and theta 3 such that the current through this terminal, this fictitious terminal is zero. Okay, but that's the other thing. So we can do this with voltage, that was done by Buttigieg, and we can also extend the same model to temperatures. Okay, in a way we are kind of measuring the local temperature around this region by weakly coupling this voltage. Okay, it would work like a thermometer, or ideal thermometer. Okay. So we apply this method to two systems. The first one is a chaotic cavity. Why chaotic cavity? Because it breaks completely all spatial symmetries. Okay. So it presents universal properties. Okay, the conductance on average is always the same. Okay, but it has fluctuations. Okay, from sample to sample. And in sample, there are fluctuations from sample to sample. So it is well described just by the mean level spacing, energy level spacing. Okay, and using random matrix theory, okay, you can do now some analytics or some empirics. Okay, we use analytical expressions which are valid, let's say, in a kind of one-over-n expansion. Okay, when the number of modes which connect this cavity is large, okay, with external resolution. So we take in the Sommerfeld expansion these conductance, these transmission coefficient terms, and then depending on whether you have magnetic field or not, then you have to consider for your random matrices, which in this case the random matrix is just a regular scattering matrix, which contains random elements. So you generate these random elements, and the only restriction is that if there's no magnetic field, then the matrices should be orthogonal. Okay? Of course, it should be also unitary in general, right? But in the presence of a magnetic field, this is the only symmetry that you can say, okay, that the matrices should be unitary. So we can put all the formulas inside, okay, and then calculate the thermopower. Okay? And now the thermopower we obtain is zero on average. Why? Because the thermopower is, in this Sommerfeld expansion, is given roughly by the derivative of the transmission divided by the transmission. Now, the transmission for chaotic cavities, you have to make an ensemble over many samples. For some samples, the derivative of the conductance is going to be positive, and for some of them it will be negative. So, on average, the thermopower is zero. Okay? But on top of this average, there are fluctuations which have a quantum origin. Okay? And the fluctuations are non-zero. Okay? And these fluctuations also depend on the coupling to the external voltage probe, to the dephasing. Okay? So the more dephasing you have, the lesser fluctuations appear. So this is demonstrating that this dephasing, let's say, is killing you with these quantum fluctuations. Okay. So now that's the last part of my talk. Now we're interested in the magnetic field symmetry of the thermopower. Why? Okay. Suppose that instead of thermopower, we are just looking at the conductance. Okay? The conductance for a two-terminal is given by this coefficient. Okay? You invert the magnetic field, you have to invert also the indices, because if the indices are the same, then the conductance is only a function of the magnetic field. Now you repeat the same calculation, but in the presence of a probe. Okay? By saying, okay, now we have dephasing, I have inelastic processes. What is the formula for the conductance? I obtain this. Okay? Now you invert the magnetic field, and then there is no magnetic field asymmetry at all. Symmetry is still even under reversal of the magnetic field orientation. Okay? Now you do the same with the thermopower. Thermopower, in the absence of the probe, in the absence of inelastic processes, is given by this equation, and then it shows this magnetic field symmetry. Okay? Now you put the probe. Okay? And then you obtain this asymmetry. Okay? Which has some formula. S of B minus S of minus B. Okay? What can we learn from this formula? This is very general. Okay? If we now make a Sommerfeld expansion, okay, the thermal conductance is given essentially by the electric conductance. Okay? This is just the Biedermann function. Okay? And then the magnetic field asymmetry just becomes zero. No symmetry. So it's a higher order effect with the Sommerfeld expansion. Okay, so it can be seen only if temperatures are of the order of the Fermi energy. Okay, so probably for macroscopic metals you could not observe this kind of asymmetries. So you have to go to nanoscopic materials, because in this case then the Fermi energy is roughly 10, 20 electron volts, and then you can have this inequalities. Okay. A motivation to study this magnetic field asymmetry appeared last year, a group of Bedenti, Saito, and Kasaki, in which they related the maximum efficiency at the maximum power in terms of both this field of magnetic, CT, and also this phi when there is a magnetic field present. Okay? If there is no magnetic field, then this maximum efficiency, the Carnot efficiency, depends only on this CT, on this field of magnetic. But in the presence of magnetic field, depends on both. So the hope is that by tuning this phi, you will be able to increase the maximum efficiency or the maximum efficiency or the efficiency at maximum power. Okay, that's something that we are investigating. Okay. Now, these are some numerical results. We did this for this system, for this ballistic junction. These 1 and 2 are the injecting leads, and this 3 is this fictitious terminal to induce incoherence. Okay, so that's my last transparency. Here we have the thermopower as a function of the Fermi energy. This is with without inelastic. Oh, sorry, this is solid. It's in the presence of inelastic or incoherent effects. Okay, so when you in absolute value, the thermopower is reduced. Okay, when you allow for these incoherent effects. Here we plot the thermopower as a function of temperature, and then we compare with the Sommerfeld approximation. Okay, and here we see that the Sommerfeld approximation is good, but only for in the limit of low temperatures. Okay, when you are in the limit of high temperatures or intermediate temperature, there is some strong deviations. Okay, and now here we have the asymmetry. The size of the asymmetry is small, okay? It's of the order of 100 smaller than the thermopower itself, okay? But still, I mean, it is non-zero, okay? You see, it is zero in the absence of inelastic processes, and it is non-zero when these incoherent effects are included, okay? And here we have the thermopower, the asymmetry as a function of temperature. Okay, it also shows a maximum, and here this an analytical fitting, which shows that the asymmetry goes as temperature to zero. Okay, but you see, in the absence of inelastic processes, the asymmetry is always zero, independently of temperature. Okay. So to conclude. I just discussed some recent experiments which have observed anisotropic thermopower in ballistic microjunctions, okay, due to asymmetry breaking a scatterer, which is put in the which is included in the around the cross point, okay. And we think that we can understand most of the features of the experiment by using a non-interacting multi-terminal transport model based on the scattering approach. And in the second part, I discuss what is the role of incoherent scattering effects in the thermopower of quantum conductors. We have checked that the Seebeck coefficient thermopower decreases when these incoherent effects are bigger or are of more importance. But however, the good news is that in these inelastic processes at high temperature, you can observe a magnetic field asymmetry of thermopower, which might be related to the maximum efficiency of these devices. Okay? And thank you for your attention.
Thank you, David. So if there are questions, comments, remarks from PT students, my priority, no? Postdocs? So any question?
How do you compute the... So everything looks like reversible thermodynamics, but you have real calculations with for this so the previous transparency here. So this calculation for isotron is so you have what is the quantum ingredient? Is the computation of the transmission coefficient?
Yes.
What is
Exactly.
you calculate this quantum mechanically,
Exactly.
and then you plug in into all the
Exactly. I mean, you calculate all the transmission coefficients and the derivative of the transmission coefficients just from essentially the regular equation. You model your sample. There are different ways to do this. You can discretize your Schrödinger equation. You can use Carbon-Shannon model. I mean, there are several ways to do this. And then from here, you can calculate the transmission. For the difficult part is to calculate the transmission. And then the rest is, as you say, you just put it into the formula.
So again, can you summarize which are the materials which are good electrical conductors and bad thermal conductors?
I mean, okay, as I said, I'm not an expert, but apparently it seems that since you have also to reduce the role of photons, so if you put interfaces, they are, I mean, if you grow like multi-layer materials, okay, these interfaces are allowed to scatter off the photons. So their contribution to the thermal conductor is not big. Okay. You cannot use an insulator either, because an insulator is a good thermal conductor.
Yes, I was looking for an example. Just
I mean, in terms of compounds, there are. I mean, the best today, I think, some bismuth telluride or something like that. Okay. But I think that the best they can do is to try to make the multi-layers of the system, to reduce the contribution of photons. As I said, so far, it's not better than 1 or 2.
So, can you increase this asymmetry not only with the inelastic scattering with the dephasing or the voltage probe, but also including some interaction effect or some chirality in the system? So this could be help to the...
If this could help the,
Yes.
let's say, I mean, we didn't, actually, we didn't study
Since
this.
there are two things done in this.
Okay, there are two different things. I mean, to have maximum
Asymmetry.
magnetic field asymmetry doesn't immediately involve that you have a maximum efficiency in the device. Because the relation is not proportional, it's some complicated nonlinear function.
But this helps.
Okay? Yes, this could help, right? But I mean, it's not that when you increase your magnetic field asymmetry, you immediately increase your efficiency. Okay, so it's I think it's still not clear how this changes. Okay. But yes, I mean, I mean, this is just a proof of concept. I mean, we say, okay, this is non-zero for this system, but we really don't care about to try to maximize this. But of course, there could be ways.
But you don't need any elastic scatter. You just need some chiral conductor with magnetic field maybe to have this asymmetry.
I don't know.
You can have both, but
Maybe, I don't know. I mean, here we just compared in the absence of this probe or in the presence of the probe. Maybe you don't need any elasticity. Maybe you need some electron interactions. Could be enough.
could be.
I don't know. Maybe.
Yeah, I have two questions. One is very simple, but I didn't get answer. Somehow you mentioned that the second move becomes more important, right?
Yes.
And,
Yeah, the second harmonic in the experiment you mean?
No, yeah, here you show.
Yes.
So what is the real explanation for this? Can you prescribe?
Oh, yeah. Okay, maybe I was a bit quick here. I mean, it's you have just your heating source, which is an AC. They put some AC around 0 voltage. Okay, so you have some time dependent voltage. Okay, so you can then you know that Joule heating is just roughly given by your resistance load. Okay. Okay, your voltage squared times your divided by your resistance load. Okay, then you have your example in this secondary circuit here, you have some resistance. This is VH for here. Right? Then you expect, of course, you generate a lot of harmonics when you have interaction in sample. But the largest is this one, just because all transport appears because the Joule heating is increasing locally the temperature in one terminal. Okay, and since you know that Joule heating is doing this, okay, then we know from Joule heating that this is proportional to temperature, at least to lowest order. Okay, and this is what you measure.
Okay.
Okay, this is e to the I omega t.
Okay.
And you square this, and then you obtain these two.
Uh-huh.
This is a bit.
And another question, which I mean, I get from you feelings that the asymmetry, the larger temperature. Is it true?
Not exactly. Here, for instance, the numerical results, we obtain some peak for intermediate temperatures. So for high temperatures, it decreases very slowly, but it decreases. I mean, in
your conclusion was something like T larger than.
Okay, moderately high temperature. Maybe I should put intermediate temperatures. Yeah, somehow.
Yeah, and maybe okay, then it's answer, but maybe because in this case, Mandel Multiterminal is okay, I mean consistent. No problem.
Yeah, no problem.
No problem.
No problem. Yes. Yeah, because all temperature. I mean, you don't specify the temperature in the conductor, you specify the temperature in the reservoirs. So it can be as high as you want.
More questions?
Thank you. Thank you.